10-step design example of a post-tensioned beam frame using ACI 318-320. I will cover the one-way slabs beams using ACI classification. The geometry and material properties will have to be validated once the member is classified into one-way slab or a beam. Then I move to define loads. After that, there will be serviceability check of the design. Then we go into minimum bonded reinforcement to be added to this section. After that, we do strength check for bending first, followed by strength check for shear. And when satisfied, we do the initial condition verification. That is when the beam is being stressed, and conclude the design by detailing. You learn the step-by-step design of a beam frame after this presentation, and review the latest ACI 318-320 for design of a beam frame. We will go through the applicable provisions. We will become familiar on the limitations on cracking imposed in ACI 318-320 and how to account for cracking in design if the design will conclude with member cracking. Then you become familiar with generation of balance loads from post-tensioning. You will get hands-on experience on the calculation of hypostatic moments which are required for safety check. So let us go through the details. Beam frames are mostly one-way slab and beam construction. This is one-way slab in the image on the right between the beams, and here between the columns through the picture we have beams with associated slab. The beam is what is being handled in this example. Typical application of beam frames is in parking structures. In typical parking structures, beams span about 60 to 65 feet. These are the way parking structures in the US are mostly configured, and they are positioned about 17 feet apart. Between them there is one-way slab. Let us continue with the geometry and definition of the system. This is an example which is breaking the columns placed on a square grid, the floor based on a square grid, into beam and slab constructions. In this example, the slab is a two-way system, whereas in the image that I showed you before, the slab is one-way system spanning between the beams. After geometry, we define the material properties, define the loads, define the design parameters, and follow it by calculating the actions, dead load moment, live load moment, and the reactions. Subsequent to that, we go into post-tensioning definition. We analyze the frame, check the frame for service condition from the analysis, and then check it for safety condition, and finally the initial condition, which is at application of jacking force. This will be the last of the three major checks, and we follow it by detailing of the design. Let us start with geometry and definition of the structural system. I have the beam framing to the column. This is the type of example we are going to deal with. Specifically here, I have selected an example where the beams are not of equal span to encounter types of unusual design situations which are uncommon, yet we encounter them every now and then, and need to be clear how best to handle it. This geometry that I have selected will result for optimum design in tendons, post-tensioning tendons being of different values in the three spans, which will require design of a condition where tendons are not all the same from one end to the next. So we are continuing on geometry and structural system. When the beam and a portion of the flange are extracted and designed in isolation, it becomes necessary to define an effective support to act with the stem in resisting the applied load. At the top right, I show a larger part of the framing. In design, it is common, not universally done, but it is common to extract from the total structure a typical beam stem along with an associated flange width, and design the member in isolation. Now, because we have bending and we have an axial force, the portion of the selected geometry which in calculation resists the bending and resists the axial force in real structure is somewhat different. At the bottom, I have shown the effective width, which is associated with bending. A smaller fraction of the flange is associated with bending. This is because of limitation in the formula that we use. In reality, the bending will spread farther, but because of the formula we used is somewhat limited, we have to also assume a limited width here to get a close answer. For axial, the precompression spreads through the entire slab, so the tributary will be applicable. There are in other presentations of this series, there is more on this topic, why the two are different and what is the correct evaluation. ACI believes, based on intuition of our former engineers, pioneers, that the bending and axial have a narrower width for spreading of the stress. But that is based on intuition. I have a presentation which deals in this series deals with that in more detail. But apart from it, the correct presentation, if we want to base the design on a representative piece of the entire structure, is what I have shown here on the right. For post-tensioning includes both bending and axial effects. The bending effects of it will be applied to this cross-section, and the axial will be applied to that. The effective width for bending and axial are different, as shown in the diagram. For axial effects, the width is the tributary of the beam stem, between halfway here and halfway there. For bending effect, ACI defines the values given in the code, typically 8 times the flange thickness on each side of the stem. If properly formulated software is used, the question of effective width does not arise. This is important. I want to repeat it. Whatever I have shown on the top right in the image is because we are going to extract a representative section of the assembly and design it in isolation using a plane frame for analysis. But if you have a software which can model this as I have shown here and analyze it with detailed finite element using theory of elasticity and engineering mechanics, this question does not arise. The question of effective width does not arise. You get the answer directly and differently. For conventionally reinforced concrete, the recommended effective width for hand calculation is based on 8 times the flange thickness on each side, or 1/4 of the span, the smaller of these, or the beam's tributary. You select the smaller of the three. This is on the assumption that you extract a section and deal with it in isolation. Based on the 3 items I just mentioned, knowing the tributary, this is the distance between the beams, so this is the total length. 16 times the flange thickness is this. 1/4 of the span is this. And for different spans, the width will be different because the spans are not equal. So span number 1, span number 2, span number 3, I have determined the quarter of the span, which is one of the limitations of the prescriptive design method, and that is what I am using. I'm following the letter of the code here, not engineering mechanics. So the tributary width will be therefore selecting from the above the 204-inch is the tributary for all spans. So for span 1 and 2, this is what I will assume, 98, and for span 3, 51 inches, 51 inches here from the third one, and 98 here from the first. So different criteria applies. Then I calculate the section properties, I mean area and second moment of area, second moment of area, moment of inertia for different spans, moment of inertia and the centroid, distance from the centroid to the top fiber, distance of the centroid to the bottom fiber. I need these section modulus, I need these when it comes to stress calculation. What we see here in this table is simply the geometry properties of the section that I assumed. Then after geometry, we go to material properties. For concrete, this is what I have assumed. For strength and weight, modulus of elasticity, creep coefficient of 2. For pre-stressing, 7-wire strand with this specification, half-inch diameter, strand area given with this value, modulus of elasticity of the strand, its ultimate strength is this. And for long-term losses, as you apply the jacking force, the force in strand will be higher than long term. With passage of time, some of the force will be lost, as well as some will be lost along the length of the tendon due to friction. So I assume that after all the losses are taken place, the stress in the strand will be 175 KSI, and I use this 175 KSI for the design. For non-pre-stressed rebar, I use 60. I have 60 KSI and 175 KSI. These are the values for the reinforcement, and the value for concrete I have here at top left. That is the strength 4000 PSI. Next, it comes to loads. There is dead load consisting of self-weight, which is based on the cross-sectional geometry and unit weight of concrete here. This is the force per foot from the slab, and this is from the stem, geometry of the stem times unit weight. So the total self-weight will be this. There will be a superimposed live load slight value for mechanical installations, if any. I have that too. So the total dead load is given based on geometry. Live load is given in the building code. I have assumed 50 pounds per square foot. The relationship, there is a relationship for reduction of live load based on the geometry of the structure, and I have used that relationship, which gives me the reduction. So I reduce the live load by 40%. That is the maximum allowable. It is based on the area over which the live load applicable to the member under question, under design, is being applied. So in this case, a live load not reduced, I have assumed 50 pounds per square foot. Next, allowable stresses. ACI defines 3 design options for allowable stresses. These are based on the tensile stress at the extreme fiber of the member, depending on the magnitude of the tensile stress at the extreme fiber. The section is defined either as uncracked or transition or cracked section, and depending on which of these stages is applicable, the serviceability design slightly differs. The decision is made on the calculated tension stress at the extreme fiber. If it is less than this amount, section is assumed to be uncracked. If it is between this and 12 square root, there is transition, defined as transition. And if it is greater than 12 square root, it is defined as cracked. This definition determines the serviceability check. But when it comes to the safety check, all the 3 stages are handled the same for determination of the rebar, if necessary, for the safety condition. But for service condition, that means deflection, we will have to follow this classification. The parking structure is assumed to be in an exposed area because that again determines the allowable stresses. Exposed area, by exposed area, open to air. Conservatively, the top surface is limited to 9 square root f prime c. We, as designer, determine what is the stress we target. I have targeted, in this example, 9 square root. 9 will bring me between transition and cracked. So in other words, there will be partial cracking as far as building code is concerned if the extreme fiber stress is 9 between initiation of cracking and this cracking there. 9 is not a code requirement. This is what I have assumed. So we continue with the design parameters. We covered the allowable tension in the previous page. Now we move to allowable compression, that is extreme fiber compressive stresses. This depends on the load condition. The code gives a value for sustained live load. Sustained live load means the live load that is likely being present during the service life of the structure. Its permissible value is this. Then you have the total load condition. That is the live load that is used in design. It may be on the member occasionally, for which the member is designed. The stress is higher because it is not always there. The significance of this compressive stress is its impact on the creep deflection of the member. Higher compression results in larger creep deflection. For this reason, we have these two values to allow less when you have a larger load. So using these coefficients, we go into calculation of bottom fiber stress and top fiber stress, which are allowable. The allowable 12 root square root f prime c, that is for, so to say, transition to cracking, and for beginning of the transition initiation we have 9. That is what I have assumed. This is the value. For initial condition, this is what the code specifies in tension. And for compression, this is the value. In other words, at time of applying the jacking force, we also calculate the extreme fiber tension and extreme fiber compression, and we make sure that the values do not exceed these permissible amounts, and if they do exceed, there is remedy in the code which I will discuss for taking care of it. For analysis, now that we have the geometry, we have the load, we use a simple frame software, simple plane frame software. I have the model shown below here, the value of the spans, and the load is defined. I use a simple frame as shown here. Note the end of the bottom supports are on a roller to allow shortening of the member from post-tensioning. Calculate the dead load moment. Select the value of the moment at the face of the support, mid-span, face of the support. Again, face of support, mid-span, face of the support. The maximum moment is not necessarily at mid-span, but for hand calculation, it is not uncommon. It is actually common to use the mid-span for code check. If you have a software, the software will most probably calculate the moment maximum where it occurs. So I have dead load moment at the top, live load moment at the bottom, and for each instance I note the value at the face of the support and midspan. Then I summarize my calculation in here. For each of the spans, span 1, span 2, span 3, the moment due to dead load, moment due to live load, and dead and live together, and the calculation of stresses due to dead and live. I tabulate it here. Next, I move to post-tensioning. For post-tensioning, I start by assuming an average precompression and target a percentage of dead load to balance. Unlike dead load and live load, that once the magnitude of the load is defined, you use the frame program. In post-tensioning, based on your judgment and based on your experience, you have to start the design by making an assumption. And depending on your judgment and the judgment of your colleague, which could be different, you end up with a different design. So here, the experience counts. Experience in design of members, post-tension, to make these two assumptions. And in this case, I have made an assumption of 150 psi. This is not by calculation, this is by assumption. And I make an assumption to target balancing 60% of the dead load. These are my inputs as design engineer, not obtained from calculation. These are inputs. Then, based on these inputs, I go into calculation. I also assume an effective long-term stress for post-tensioning. This is after jacking and passage of time, allowing for shrinkage, allowing for friction loss between the strand and its sheathing. 175 KSI for unbonded tendons and 160 for bonded tendons. I have used in this example 175 unbonded tendons for unbonded tendons. So each strand has this cross section. Its final stress is this. So the force per strand will be 26.77 kips. I use this 20 for the design. And based on this value, 26.77, I determine the number of strands needed for initial calculation, based obviously on the percentage of the dead loads that I want to balance. For bonded tendons, a smaller value, 160 KSI, is assumed. So for each strand, I end up with a smaller effective force of 24.48. Now, I have to select the number of strands so that I know the force before I go into calculation of the demand force by post-tensioning. I have the cross-sectional area of the member. I have assumed 150 psi average compression multiplied by cross-sectional area. That gives me the total post-tensioning force I need for span number 1. I divide it by the force that each strand provides. I get the number of strands required. 8.24 isn't a round number. I assume 9 strands. The force of 9 strands will be this much, 9 times the force of each strand. With 9 strands, and I form the so to say, arrangement of the tendons, having the knowing the position at the top and the position at the end, and also the high point. I have to calculate the balance load from the tendons, and I have shown this diagram in which I have a change in cross section, and I have more strands in one span coming to terminating in the shorter span. I need to account for this drop of slab or member thickness, also for the extension of tendon coming from one span over into the next. The balance loads from this tendon arrangement consists of force normal to the centroid, that means pre-compression, along with member's center line, causing forces along the member's center line cause uniform precompression. So I have uniform precompression for force along the center, but also bending moment because of change in centroid. So there is a moment and there is axial resulting from the arrangement I have shown. Moments are at locations of change in centroidal axis. In this figure, the balance load from post-tensioning consists of all the three components mentioned here. Consists of axial, change in centroidal axis, and extension of tendon terminating somewhere along the length of the span. We have all the three conditions. I use simple parabola, and for simple parabola, the relationship is given here. The force of the simple parabola is axial, downward at the end, and upward, assumed uniform. In reality, it is very close to uniform, but for calculation, we assume uniform upward force. And for the example that I have shown the values at the bottom right. I have the value A, B, and L, A, B, and L. I can use the formula here to give me the position of the low point from the formula, and having the position of the low point, I use this relationship, which is here, to give me the uplift from the post-tensioning. This uplift provides 51% fraction of self-weight upward force. It is less than 60. My target was to provide 60%. So I have to increase the number of strands in order to arrive at 60% uplift. That is my target. to arrive at 60%, I need to go to 10.6 strands, which wouldn't work because it's a fraction. So I select 12 strands. 12 strands will give me this uplift, which is 68%. It is acceptable. I targeted 60, now I have 68%. It is not always possible to get the exact percentage that you wish. That's also not very critical, the exact number. Now, what about the strands that terminate from one span into the next? The relationship is shown here. I assume that the strands extend into the next span by about 1/5 of the span. 1/5 of the span. There will be an upward and downward force which are given by these relationships. I have the length of the span as 55 feet. The extension of the strand is over 1/5 of the span, and I have that extension. Use the formula here to get the concentrated load to be this much. So coming back to the full geometry, I determine the forces that the post-tensioning applies to the member. They consist of up and down forces. Here are the number of strands and the force from the post-tensioning, and below the upward and downward forces from the post-tensioning. I validate the calculation of balance load up and down forces. I want to make sure that I have done it correctly before moving ahead. This is the member, these are the number of strands, and this is up and down forces. Balance load needs to be validated before I apply it to the member. The sum of forces must be 0. The balance loads must be in equilibrium. Post-tensioning tendons always apply forces to the member that are in equilibrium, always, in all the cases. So what I do, I add up these up and down forces in this relationship. I sum them up and they add up to be 0. So it is the correct representation of this geometry. Some of the moments also, it is up and down forces, but also I take moments about the first support. I take moments of these forces about here, and the moment sum is essentially 0. This little small value is due to the approximations in the number of digits. So I accept it to be correct because it is very small compared to the value of the items in the formula. The outcome within approximation of numerical calculations, so it is okay. Calculate the post-tensioning actions now. We calculate the post-tensioning moments and reactions by applying the balance load that I showed at the bottom right of the previous slide to the member. For hand calculation, we note the values of the moments at the face of the support and midspan, and the reactions of post-tensioning at the supports. We can note the reactions from post-tensioning for the purpose of later calculating the hyperstatic moments along the member. At the top right, I have the moment of post-tensioning forces, and in the middle, the reactions from post-tensioning at the supports. These reactions are the hyperstatic actions. I need the hyperstatic actions when I go into safety check. And from hyperstatic actions, I form a bending moment diagram. Here, this bending moment is the same as this bending moment. And here, this moment is equal to these actions multiplied by this distance. This is how I form the bending moment diagram of hyperstatic actions. Now I can do deflection check. Deflection check from dead load is this much. From post-tensioning is this much. From a live load is this much. So I have 3 action components, each of which gives me a value for deflection. The first check I do is to validate the design based on live load deflection. The live load deflection is based from the calculation on elastic solution. But since we are in the transition, we have initiated cracking, the design was based for allowable stress exceeding 7 root of prime C, but less than 12, there would be partial cracking, which will impact the deflection. So the procedure is simple. We first calculate the deflection for this transition condition as if the member is not cracked, and then magnify the deflection by a coefficient which depends on the anticipated amount of cracking and its impact on the calculated deflection. So we have to allow for cracking because we are dealing in the transition period. The calculation will be adjusted based on the anticipated amount of cracking. ACI permits the elastically calculated deflection. The elastically calculated deflection, I should add another note to it, based on gross cross-section. That means we assume the entire section effective, but we magnify it by a coefficient if the extreme fiber does not exceed this value. If the extreme fiber calculated between 6 and 12, it is permissible to magnify the calculated deflection by a coefficient. If it is more than 12 root square f prime c, we have to go into more rigorous calculation. In this case, the effective moment of inertia will be a fraction of the gross moment of inertia. Moment of inertia, or second moment of area, is what we used in calculating the deflection, but we are going to reduce it based on the magnitude of the extreme feeder maximum stress. That is the relationship. I substitute the numerical values and I come out with 0.78. In other words, we magnify the deflection based on its calculated value divided by this 0.78. So the adjusted deflection will be the calculated divided by this 0.78. That is the live load deflection. Why is this repeated? But that is fine. So live load deflection divided by the span is this ratio. It is 1 over this amount of the span. Much, much smaller than the value permissible by the code. The code says live load deflection shall not exceed span over 360. No, we have much less deflection here, so it is okay. The long-term deflection, that was instantaneous. The long-term deflection is the immediate deflection allowing creep factor of 2. For creep factor becoming effective, we assume that in a load combination there will be 30% of live load, of design live load, be applicable. For long-term calculation of deflection, we recognize that the live load is not on the member all the time. It will be on the member for a fraction of the time. This 0.3 is not given in the code. I have taken it from the European code, 0.3 of the live load. So the formula for long-term deflection is 1 times Z, 1 times PT, 30% of live load, 1 is immediate deflection, multiplied by plus 2 times creep deflection. I enter the values in this formula and come up with deflection of 1.24, divided by the compare it with the span length, and I see it is 1 over 619. That is the live load deflection. 1 over 2. I see I have here taken 1 over 250. Actually, ACI says 1 over 240. This 250 is the European code. In any event, it is acceptable. It should not exceed 1 over 240, not 250. Then we do stress check. I did deflection check due to live load. Why did I do deflection check to live load first before going to stress check? Because if live load deflection is not met, you have to change the design. You have to redesign to make the live load deflection satisfied. There is no remedy. If you use European code and on a number of other codes, there is remedy. Remedy is putting rebar where cracks form. Then we go to stress check. Stress check is dead live post-tensioning moment divided by section modulus to give you the extreme fiber and precompression. This is the section modulus. I have the values here for top and bottom, and I have the area here. Average precompression is known, so I can form the extreme fiber stresses for various locations for different loads and at different locations. The calculated stress, the allowable stress, and we see whether the calculated is within the allowable at points that I have selected along the member at the face of the support and at midspan, and all seem they all are okay based on the sustained and total load that I have. Next is to put minimum reinforcement that the code requires. There is a flow chart here which shows for unbonded you need that much reinforcement, for bonded you need this. These circles refer to the detailed explanation of each of these requirements, given some here, some in the book at the end. We are dealing in this example with unbonded, and at unbonded we have at the top of the support rebar and in the span at the bottom rebar. Here we have in span at the bottom. At the top and at the bottom, the area of rebar, bonded reinforcement I should say, is this much. Coefficient times the tensile area of the section. By tensile area, I mean if this is the centroidal axis, this is the tension at midspan. If you have a beam and slab combination, as is our case, the hatched section is the area which is to be placed here, area of tension. This coefficient times area of tension gives the amount of rebar to be placed within the tensile zone. This is again the area. This will be placed at the top and bottom, wherever you have the tension. Over the support, typically you have tension at the top, so this will be placed at the top, and toward the center of the span, it is at the bottom, you put it at the bottom. So at supports 1, 2, and 3, this will be the amount of area based on the geometry. I use this bar size, and the total number required is 4 bar size number 7 bar. The area provided is okay. Then I go to safety check. I put the minimum rebar first because the minimum rebar contributes to the member capacity and will be beneficial when we go to safety check right now. The load combination for safety check is this and this. There are 2 load combinations to go through. The second one rarely governs. You notice here that in the load combination, now you have hyperstatic actions. For service condition, you had PT action. For Safety, you have hyperstatic. The hyperstatic moments are shown in here. These are the reactions of post-tensioning at the connection to the supports, moments and axials. The reactions, these values, are used to build the moment diagram. They result in distribution of moment along the length of the member. Here I have this bending moment, which is the same as here, 75, 75. And so on. I note the value of the moment at the face of the support and the midspan for check. Dead load moment, live load moment, and the hyperstatic. Hyperstatic at different points. These are selected points at the face of the support and at midspan. With these moments known, I can form the demand based on this load combination. The strength adequacy of the section at the selected points is based on the existing post-tensioning and a minimum reinforcement, and it is verified. In other words, what I say here is rather than calculating the required amount of reinforcement for the demand values shown here, you bring the argument that you already have post-tensioning, you already have rebar over the support and at midspan. Those provide a minimum, a certain amount of capacity. Let us calculate the capacity and compare it with demand. Where capacity is short of demand, at that location we add rebar. This is much simpler than to start by calculating the required rebar and comparing it with the existing. Then we go to one-way shear design. After we check for safety, we have to do shear check. For shear check, we use the same load combination, dead, live, and hyperstatic, and ACI permits to initiate section for shear check at the half the height of the member from face of the support. In other words, we disregard a very, very small section of the member for shear check. And then we break the distribution of shear along the member into three regions. ACI bases the design on three regions. This is the shear distribution, and it will be broken into three regions. The three regions exceed, I have to show it here. The first region is where demand exceeds allowable value. Then obviously you have to put calculated reinforcement. That is region 1. In this distribution, the region 1 of it is where the shear demand exceeds the allowable value. Region 2, where the demand is less than allowable, but more than 50%. Region 2 will probably be here, where the demand is is less than allowable, but more than half of it. And the third region is where the demand is less than one half of the allowable. Each of these regions will be designed differently. We reinforce each region accordingly. I have shown here the breakdown. Number one, a narrow strip here will be disregarded, and that narrow strip is right adjacent to the face of support. Then the three regions are here. This exceeds the allowable. This is the region that is exceeding half the allowable, and this is the region less than half the allowable. Each one is designed differently. After we do the shear design, we go to initial condition. Initial condition is evaluation of the member at jacking at the time the post tensioning is being applied. The load combination is not given in the code, but the common value is this: 1 time dead and 1.1 time post tensioning, assuming live load is not there yet and the post tensioning is more than what is in the previously design we went to, because the losses due to post-tensioning have not been taken care, have not materialized. You reinforce where the calculated extreme fiber tension exceeds the allowable value. You wait until concrete gains adequate strength where calculated extreme fiber compression exceeds the allowable value. At stressing, concrete does not have its matured strength, so in this case 3000 psi is specified at the strength when concrete is stressed. The allowable values are this amount for tension and this amount for compression. These are the extreme fiber allowable values. Initial values are checked and found to satisfy the requirements. Last is detailing. Detailing consists of length of the bar were either required by minimum values or calculation, and the length of the bars are shown here for the example which we have gone through. You have rebar at the bottom and rebar at the top. In summary, we started by defining the geometry and the structural system. Define material properties, concrete strength, post-tensioning strength, allowable values, defined loads, and defined design parameters. By design parameters, I mean how much pre-compression, what percentage of dead load to balance, what are the allowable extreme fiber stresses. Then we calculated the demand values due to dead load moment, live load moment. We then moved into post-tensioning selection, assumed a percentage of self-weight to be balanced, and calculated the required number of rebars. We analyzed the frame. We checked for live load deflection because, as I mentioned, that is a must satisfy requirement. Then we checked for serviceability, minimum requirements, minimum rebar, and followed it with a safety check. In safety check, I emphasized that we calculate the capacity of each section and compare it with demand. And all concluded with initial condition, stresses, extreme fiber stresses at time of jacking, and did detailing the length reinforcement at the top and reinforcement at the bottom. Thank you for listening. The material presented here was extracted from a chapter of this book.